Hello, my name is Sophie Hawthorne, and today I would like to discuss ionization energy from Module 4, Atoms. The ionization energy of an atom came to be because of Dmitry Mendeleev's work, who is often denoted the father of the periodic table. Organization was based on increasing relative atomic weight. Meanwhile, groups or vertical columns were organized together as they all possess similar physical and chemical properties.
First ionization energy can be defined as the amount of energy in kilojoules per mole that 1 mole of a gaseous atom must absorb to lose 1 mole of electrons.
Since energy input is always required, the ionization energy must be positive and endothermic. A larger ionization energy means the electron is more tightly bound. The second ionization energy is the amount of energy in kilojoules per mole that 1 mole of a gaseous ion opposed to an atom, since it's been previously ionized, must absorb to lose 1 mole of electrons. The equation for first ionization energy can be written as follows. A gaseous sodium atom loses 1 electron, creating a sodium ion. Likewise, the equation for a second ionization energy can be written with a sodium ion, which loses an electron, creating sodium with a 2+ charge. Now, there are 3 factors that impact ionization energy. Firstly is distance. Now, as the distance from the nucleus increases, ionization energy decreases. Next is shielding. Electrons that are shielded or further away from the nucleus have a decreased ionization energy. So with an increase in shielding, decrease ionization energy. Lastly is nuclear charge. Now, as the charge increases, the ionization energy increases as well. Now here we have a periodic table. Now, when we go up a group, the ionization energy also increases. Here we can see that sodium has an electron configuration of 3s1. The valence electron in sodium is further away from the nucleus than the valence electron in the 2s1 orbital of lithium. Na also is a larger atom than lithium and has a greater atomic radius. Therefore, sodium's electrons are further from the nucleus. Next is because of shielding. Electrons that are further away from the nucleus have more shielding, therefore lower ionization energy. If we see here, sodium has 10 electrons in its inner core and 1 valence electron. Lithium, on the other hand, has 2 inner core electrons and the same 1 valence electron. This means that lithium has less inner core electrons to shield its valence electron from the nucleus. The next trend is an increase of ionization energy from left to right across the periods. So here we have the nuclear charge increasing. Therefore, the ionization energy increases as well. We've already circled here that sodium has a nuclear charge of 11 versus argon has a nuclear charge of 18. When nuclear charge increases, ionization energy increases as well, since there are more protons with attractive forces to the nucleus. So as we know, periodic trends coexist. So as atomic radius decreases, ionization energy increases. With a large atom, distance to the nucleus is greater, and there is more shielding from inner core electrons. More energy is then required to remove an electron, as they're more equally attracted to the nucleus and tightly bound. So we can say as well, as nuclear charge increases, ionization energy increases. From the periodic table, we can see that noble gases are the hardest to rid of an electron, and alkali metals are the easiest to remove an electron. This is because noble gases, with the exception of helium, who only has 2 electrons in their valence shell, Noble gases in their lowest state have the maximum number of electrons in their valence shell that is permitted. Noble gases have an ideal electron configuration of N2s6, making them very stable, and altercation is difficult. Alkali metals, on the other hand, have one valence electron in their outer shell, an electron configuration of Ns1. Alkali metals are more willing to lose one electron to become more stable, as they will then have the same electron configuration of a noble gas. We can say that an element with a lower ionization energy is more reactive. So, due to Slater's rule stating that each electron will experience less than the actual nuclear charge because of shielding of other electrons, when an electron is shielded by another electron that is closer to the nucleus, its ionization energy decreases. Each time an electron is removed, there is one more proton in the nucleus. The positive charge is no longer balanced by a negatively charged electron, and the relative nuclear charge is increasingly positive. With an increase in relative nuclear charge, the remaining electrons are more attracted to the nucleus. This increases the difficulty of removing the next electron. Therefore, successive ionization energy of an element increases steadily. When a core electron is removed, there will be a large positive spike in ionization energy compared to when removing valence electrons. So here we have the successive ionization energy of sodium. And this can be broken down into here the 3s orbital. Here we'll have the 2s and the 2p orbitals, and up top the 1s. As we can see, the ionization energy of sodium is lowest for the 3s shell. However, there's a large jump of increasing ionization energy at each level. So we have one level jump here and another level jump there. And this is because the distance from the nucleus is decreasing. An electron is being removed from more positive ion at each level, and this is a steadily increases during its own sublevel. And again, as shown here on the electron configuration chart of sodium, at the 3s shell, it's the most simple to remove an electron. And then there's a large jump of increasing ionization energy to the 2p orbital, where the energy will steadily increase in the sublevel. And then there'll be another large jump to the 1s orbital, which is the closest
So there are
to
a
the
few
nucleus that we can
exceptions
show
going
here
across
at the
the
bottom.
period. An example of one of those exceptions is magnesium to aluminum.
So magnesium has an electron configuration of 3s2 versus aluminum has an electron configuration of 3p1. So the p level is further away from the nucleus and has more shielding than 3s2, therefore requires less ionization energy to remove an electron. Next, across the period again, is phosphorus to sulfur. So phosphorus electron configuration is 3p3 and sulfur's is 3p4. Now, it's easier to remove an electron from 3p4 because of electron-electron repulsion. Electrons are more stable when unpaired or half-filled, as proven by Hund's rule. So an increase in stability means a decrease in energy for the electron, therefore making it further away from the nucleus and easier to remove. So we can state that it's easier to remove paired electrons than unpaired, meaning a lower ionization energy. From the periodic table, we can see that noble gases are the hardest to rid of an electron, and alkali metals are the easiest to remove an electron. This is because noble gases, with the exception of helium, who only has 2 electrons in their valence shell, noble gases in their lowest state have the maximum number of electrons in their valence shell that is permitted. Noble gases have an ideal electron configuration of N2s6, making them very stable, and altercation is difficult. Alkali metals, on the other hand, have one valence electron in their outer shell, an electron configuration of Ns1. Alkali metals are more willing to lose one electron to become more stable, as they will then have the same electron configuration of a noble gas. We can say that an element with a lower ionization energy is more reactive.